Right, so we're dealing with that special circumstance where they stay the same length. All right. All right. Like I said, we're going to go through, we're going to do some more talking about what centripetal motion is. But first, we're going to do a rumors. We've done this before. So we've got a ball traveling around in a circle, and it's being held in place by a string, and the string's going to break. So the question is, which path will the ball take after the string is broken? Now, to help prompt you on how I want you to answer this on your Post-it note, I want you to write, I think path, and then you pick A, B, C, or D, and then because, and whatever your reasoning is. You might talk about one of Newton's laws, you might talk about what we did on Wednesday, right? But that's how I want you to answer this.
I don't think you'll go anywhere.
If you don't, if you think it'll be something other than A, B, C, or D, just pick the one that'll be closest. I think that these four choices cover the majority of possibilities. Okay, so again, on your Post-it, you're writing your name and which path that you think that it is. You're welcome. All right, so I'll give you 1 minute to decide on the path that you think it is. This is an independent thing. Just write down what you think to start. Again, this is an independent part for right now. Just write down which path that you think it is, A, B, C, or D. Yep, so you'll write your name on the top of the Post-it as well. So your name, and then which path you think it is and why. So it's going around on the string, and then we break the string. The string gets cut or breaks. So from this point on, the string is no longer attached. It was no longer in one piece. So what's it going to do? A, B, C, or D?
Why would it curve that?
So, right. So it's spinning around on the string, right? And then at the moment shown, the string just breaks. Now I'm going to show this to you using the hoop. I have a video of it. So you'll get to see this in motion actually happen. But I want to get your predictions first. So what you'll do now is, just so we can go a little bit quicker, I'll give you 3 minutes. You're going to get up, move around the room. You're going to exchange your idea, right? I want you to say which path you think it is, and why, and then exchange with the person. So every time you exchange, you're talking about what is written on the Post-it you currently have. And at the end, I'm going to have you come on up and put your Post-it in 4 corners here to represent A, B, C, and D. So that'll happen when the beep goes off after 3 minutes, right? So you got 3 minutes. Get them up. You can leave your stuff where you are. All right, so spread your rumors. So standing up, you're moving around the room. Okay, you're trading, you're reading what you wrote, and you're switching it with someone else. Okay, you're writing, I think path blank because blank. Oops, sorry. All right, once you've switched with at least 3 other people, you can bring yours up and stick it in the corner on the front there. A, B, C, or D. All right, so again, you're moving, you're sticking your post-it in the corner, A, B, C, or D.
I got the.
Think D? Okay. What do you think?
Okay, we think.
I don't.
Okay.
I'm not telling you which one it is.
This is what we think is C because, well, it still has
Set up
like
there.
leftover force, but it's like going the same way, bro, kind of.
Wait, so you're saying you think it's D?
Yeah.
What do you think it is?
I think it's B.
B?
Yeah,
Okay.
because it's in the middle going around the circle, so there's
Awesome.
leftover force almost, and it
All right. So we've got. So it looks like we're pretty much split between B and C. B and C. So paths B and C. I don't think anyone did. Anyone put A? I didn't. No one stuck any A up here. You put A? Oh. Oh no, this is just another A, a big A. Natalie, you wrote. Oh, okay. A. All right, so one person for A, got a couple people for D, but mainly between B and C. So let's watch some data, and then we'll see if you can explain why it is the path that it is. All right, so this is a video. This is a video that I recorded at home. The duct tape line there is just to show you what direction path C would be. So it's just like a reference line. So this will be the tangent to this part of the hoop. And what I'm gonna do is I'm not gonna cut a string, of course, because it's this hoop. I'm just gonna lift it up. If I lift it up, what should happen to the normal force?
You have to lift it up exactly on time.
I did a really good job. It took a few takes, but I promise I did it right. I promise I did it right. Okay. The other thing that I have on here, the other thing that I have in here from Tracker are the velocity vectors. Right? Remember how it can calculate that for us. So you'll see some red lines up here. It's just more confirmation that the velocity is in fact tangent. I did it for the acceleration, but if you remember, the acceleration graph is really jumpy. So a lot of the acceleration is pointed towards the center, but they jump around a little bit. I don't want to visually distract you. So the video will go around in the circle a couple of times. I think it goes around 3 times. And then finally, I lift up the hoop, and you'll see what direction the marble goes. Okay, here we go.
What?
What? Hold on. Let's watch this again. Just watch this again. So what path is that?
Technically speaking,
Technically,
it goes straight. It's called human error. He
Yeah.
does it by hand, so
it goes,
let's see.
yes. The answer is path C. There is a slight little curve at the end. That's because it's a New York City apartment and the floors aren't straight. So it curves a little bit at the end. But the answer is C. The answer is C. So before we talk about why it's C, we're going to take a minute, think about why it might be answer C. Take a minute. Let me see if I can get it.
Did you do another video with 2 minutes got another point? Because I would love to see that to see the better room.
To see what?
Because my thing is, remember how we have the velocity line? So my thing is, you know how your tracker shows the velocity line, right?
Right.
So my thing is, whenever you release it, the ball will go in the direction like that.
Well, it should go in the release, so it goes off in a straight line. Yeah.
You know what I'm saying? It's always
So let's look.
a straight line because it's a circle. It doesn't have
Hold on. So what about why does the ball travel in a circle in the first place? Because it's inside the hoop, but what interaction between the hoop and the marble takes place? There's a normal force. The whole time the marble or this ball is traveling in a circle, it is accelerating. The whole time it's going around that circle, it's accelerating. There must be a force for there to be acceleration. That is Newton's. Melissa, which law is that? That for there to be an acceleration, there must be a force. Yeah, it's Newton's first law. Okay? It's Newton's first law. What is the net force when we cut the string? Erica, what would the net force be once we cut the string? If I'm pulling on something with a string and then the string breaks, the force goes away. Right? So once the string is cut or the hoop is removed, the net force becomes 0. If the net force is 0, can the acceleration be not 0? No. If F is 0, A is 0. That's Newton's first law. F is 0, A is 0. Now, the rest of Newton's first law tells us what the motion of an object should be if there is no forces acting on it. It must travel in a straight line with constant velocity. And that's what we see here. The ball doesn't remember that it was traveling in a circle up until this point and tries to take a curved path, right? It's not like breaking the string pushes the ball so it takes path D. It just keeps going in a straight line like nothing happened at all. Because at that moment, it was traveling in a straight line and no more forces, so it will now travel in a straight line. Daniel.
And if you were to measure its speed with the speed that it travels inside the circle be the same. That's what has to be
It should be exactly the same, right? So this is an example of it being in horizontal motion. So there's no reason why it should speed up or slow down. And once you remove the force, there's no acceleration. So it will not speed up or slow down. This is the exact same thing that would happen if the sun suddenly disappeared. If the sun suddenly disappeared and there was no gravity keeping the earth going in a circle, it would just fly off in a straight line. Constant speed in a straight line. It would stop going in a circle, right? So this is a common kind. I've seen this question a couple times before on the reasoning exam, where they, just like here, you have these 4 different options, and you're asked to say, what direction would it go once the string is broken, the gravity goes away. I mean, they could word it in different ways, but once there is no force, we end up with no longer traveling in a circle. Right. The other thing I want to look at before we do our clicker questions is Daniel, I think it was Daniel, had brought up, what about if you're traveling over the top of a hill? Is that also traveling in circular motion? And
Yes.
it is, right? Because this car is trying to travel, it's not a full circle, but it's like this crest of a circle. Exactly. So let's see if we can verify, what's going on here. So I'm going to draw a free body diagram of the car. Okay. What is one of the forces acting on it? Daily, what would be one force acting on the car? So let's see, is the car touching anything? Grand. So when two things touch, what kind of force is there? The name of the force when two things touch. There would be that too. Give her some time. While Nelly's looking up what the name of that force is, Remy, what other forces they're acting on the car? Gravity. What direction does that act? Okay, so that would be equal to the mass of the car times g. Okay, so that would be weight. That would be weight pulling down on the car. Nelly, what's that other force named? The normal force. Okay, so there would also be a normal force. And what direction would that point? Up, right? Because the ground is pushing up on. Well, they don't necessarily have to be the same. If they were the same, what would the acceleration be? 0. If this plus this equals, are they the same length, opposite directions, we'd get 0.
And it's not going to be the same.
In this case, it won't be. Oh, yes, it won't be the same. So what I'm going to do is I'm going to draw the C direction. That points from the car down towards the center of the circle. And I'm going to add up the forces in the C direction, and that's going to equal A, hold on, so that's going to equal M times A in the C direction. This is just Newton's second law. I'm saying positive points down towards the center of the circle that the car is traveling in. Holly? So I've chosen the wheels to be a part of the car. There is a force between the wheels because of friction. That's going to point, tangent. So that when we add it up, we wouldn't include it because it doesn't point in the C direction. So all I'm doing now is I'm going to do Newton's second law in the C direction. I got to decide, should I add or subtract these two forces? All right, so Aji, what do you think? Should I add the normal force or subtract the normal force based off of the coordinate system? So if I were to add the normal force, that means it points in the same direction as positive C. So we want to subtract it, so I would do minus the normal force. How about the weight? Lauren, what do you think I should do with the weight? Add or subtract? Add. Why do I add it? So we subtracted the normal force because it was in the opposite direction. So why do I add weight? Because it's in the same direction. So plus mg equals, I got m. And what is the centripetal acceleration equal to according to our formula? Shakira, look in your notes. What's the formula for centripetal acceleration? This is what we did on Wednesday. Oh, we need someone to help Shakira out. Let's see. Oh, Lauren also wasn't here. Kayla, help us out. What is the centripetal acceleration equal to? Yeah. So if we're traveling in the circle, there must be centripetal acceleration v squared over r. The radius would be this, however, you could have a really steep curve, like hill, or a very flat one, right? The flatter the crest of the hill is, the bigger r is. The steeper the top of the curve is, the smaller r is.
So when we're measuring it, we're only measuring it from the point where the car is stopped, right? Because
No.
my thing is the car goes up and then over, the acceleration goes from down and then up.
Nope, so this acceleration the whole time, it's kind of like with concavity. So this is negative concavity, so the curvature is always a positive number. Yes, a curve in real life might be more steep here and less steep there. That's what like a real hill would look like.
Don't say when the car will go down faster than when it went out over the hill.
Yeah.
That was, so you can also accelerate in the direction you're traveling. We're assuming that the speed is the same the whole time. They're stepping on the gas on the way over the hill. They're taking their foot off the gas on the way down. Right, in real life, the velocity would change depending on where you are. Here we're just saying that it's a constant. Okay. Well, that's a fair point. So what I'm going to do with this step is I'm going to solve for the normal force. So I'm going to say, I'm going to add the normal force to both sides, and I'm going to subtract mv squared over r from both sides. So I want to figure out what is the normal force. The normal force is equal to mg minus mv squared over r. All I've done is I said, I wonder how big the normal force is. I could plug in numbers. If I knew the mass of the car, how fast it was going in this radius of the hill, I could figure this out. But we don't need exact numbers. We're going to think of three different situations. The first situation is what is the normal force when V equals 0? What would the normal force be when V equals 0? Betsy, what would the normal force be when V equals 0? Yeah, it would be normal force equals mg. That means if we're not traveling in a circle, if V is 0, if the car is at rest, the weight and the normal force have the same magnitude. We're not traveling in a circle. We don't need there to be a centripetal acceleration. But that's the first question Daniel started with, right? We said, oh, if they're equal, the acceleration should be 0. Acceleration 0, not traveling in a circle. What about when V is greater than 0? The normal force, is it greater than mg, less than mg, or equal to mg? Landriana, is it equal to mg, greater than mg, or less than mg?
I know it's not equal to mg.
Good, so it's definitely not equal. Why isn't it equal?
Because if it's equal to 0, it's equal to mg.
Okay. What am I do? So this would be some number. By adding it, subtracting it. Yeah, it would be less than. The normal force would be less than mg. Maybe you've experienced this driving around in a car or a bus. Goes over the top of a hill, you feel a little bit lighter. The normal force goes down. What happens though when the car goes not over the top of the hill, but at the bottom of the hill? It's the opposite effect, right? So if you're going on the bottom of the hill like this, what has changed is the direction of the center of the circle. Now the center of the circle points up. If you're at the top of the hill, the center of the circle points down. If you're at the bottom of the hill, the center of the circle points up. So this minus sign turns into a plus sign. And so you end up feeling heavier at the bottom of a hill and lighter at the top. So every once in a while, they'll ask a question where they'll give you a picture like this, and they'll ask what happens to the normal force. So if you are going over the top of the hill, the normal force goes down. And if you're at the bottom of the hill, a normal force goes up. Okay? So I want to show you another situation where centripetal acceleration applies. Right? Doesn't matter why you're going in a circle, whether you're being spun around on a string or in a loop-de-loop, in a car, over the top of a hill, you're a planet. As long as you're traveling in a circle, you must have the centripetal acceleration. Right? And again, you'll see a couple different examples of this on the homework that is due on Wednesday. All right. All right, so I'm gonna go around and pass out the Plicker cards. And while I'm doing that, I want you to think about this question here. Okay. All right, so we've got if the mass of an object undergoing uniform circular motion is doubled, the magnitude of the cart's acceleration would be, is it unchanged, doubled, halved, or quadrupled? All right, so again, A, B, C, or D, rotate your card to show your answer. You hold it up and I will scan it. Do you want to change your answer?
No, it's okay. It's either that or my other.
It's either that or wow, so
It's either this or this, I think.
oh yes, I'm so.
I think it's one of these two.
Can I change my answer?
Yeah.
No.
I'll just move your finger. There you go.
So then my thing is gonna be this. Never mind.
A few more people.
You can switch it.
Yeah.
Yeah, you can switch your answer if you turn it. Let's move your fingers, Vicky. There you go. Who are you still waiting for? Let's see. Tree, I don't have yours yet. What are you thinking? Okay. Let's take 30 more seconds.
I don't get you. When he could get you, he never gets you. And then when you actually
All right. All right. So let's see. All right, Soraya, talk to us about which one you picked and why you picked it. Okay. Hmm? So, okay, all right, so if we increase the mass, we should end up with more. It's okay. And let's see, let's have, all right, Melanie, I see you went with A, unchanged. Why did you pick A unchanged? That's okay. Okay. Sure. So let's look at the graph here. And the answer is A.
Why do I listen to you?
So big shout out to my table in the middle there for getting it. Let's write down what is the formula for centripetal acceleration? It is v squared over r. Nowhere in that formula does mass appear. Okay? Nowhere in that formula does mass appear. So this formula tells you the value of the centripetal acceleration, that it is v squared over r.
Do you have another question for me?
Lord, I have second. Yeah. How did you think of it? Well, there is another formula that can get you thinking that according to Newton's second law, right.
I also thought.
But let's think about it. If all I'm doing is changing the mass, that doesn't mean I didn't change the force. Right? I can see you arguing, oh, well, maybe the question's not very clear. But as long as it is still traveling at the same speed, at the same radius, whether it's a small mass or a large mass, what does it need more of? It does need more force. So if you went with doubled, you've answered the question, the magnitude of the cart's net force. That definitely would double. But that wasn't the question was just about the centripetal acceleration. So as long as the v is the same and the r is the same, it ends up with the same acceleration. Daniel.
I wasn't here for that lesson, so I didn't think about the equation. But I sort of thought of it like that. But in the sense of, I was thinking about when we did the lesson on weight and mass.
Okay.
And the things that they, like, you're talking about the things where they affect weight. So I just don't remember speaking about acceleration necessarily to this extent.
Well, if you think about Newton's second law, if I take the same amount of force by increase the mass, I would get less acceleration, right? So, but because this question says we're traveling in the same circle, it doesn't say anything about the speed changing or the r changing. So it's got to be the same centripetal acceleration. This is a tricky question, right? If we went down the street, if we went over to Columbia and visited the physics professors there, and we asked them this question, right, they might not get it right because they might not think of it in the right way, right? This is a tricky question. Don't feel bad because you didn't get this one. But what you want to pay attention for is for questions like this, unless they tell you it changes, it stays the same. So because this question didn't say anything about v or r changing, they must have stayed the same. All right, let's try another question. All right. So the centripetal acceleration of a ball moving at a constant speed in a horizontal circular path, is it 0? Is it constant in direction but changing in magnitude? Constant in magnitude but changing in direction? Or changing in both magnitude and direction?
Damn, son, let me just read that to myself real quick.
Yeah, take a second to read it. Again, I'm trying to get you familiar with the style of question they've asked before. So think about when you talk about a vector, its magnitude and its direction. What does magnitude mean when you talk about a vector? Right, every vector has a magnitude, like acceleration.
So you said horizontal. Is it
So that would be like this. This should be an example of horizontal. It's describing this situation. What about it stays the same? Remember, we're talking about a vector. It's got magnitude and direction. Okay, it's got magnitude and direction.
I'm probably wrong, but with the right reason.
Did you put?
I didn't want to say it.
No, just so.
Again, we're talking about magnitude and direction.
I don't think it was zero.
Just move your hand down, Erica. You're blocking the thing. All right, who else still needs to be? Oh, it's my wife. Anyone else? Okay, I got yours.
Please be zero.
You're telling me not to jinx it?
All right, I get yours. All right. All right. So the first thing I want to do is let's go through and cross out. Oh, we can. Wow, we can get rid of 3 of them. So the first one we definitely want to cross out is which one? Let's see. Natalie, which one is definitely not true? Which one is that you definitely know the acceleration is not equal to? Yeah, it's definitely not equal to 0, right? Because if it's traveling in a circle, it's got to have centripetal acceleration. So you can definitely cross out A. Okay? So if you're thinking, if you went with A, think about it. As soon as you see circular path, you got to get rid of 0 acceleration. It's got to accelerate or it can't go in a circle. All right, the next thing to think about is this constant speed part. What is true about the magnitude of the acceleration? If the speed is constant, it's constant. The magnitude of the acceleration is constant. So let's see. B, but changing in magnitude. Let's see. Changing in magnitude, and so we're left with C. All right? Okay. So let's see. All right, so great job. Most people got C. So again, the thing you want, got just a couple more minutes. Right? Even though we say the acceleration always points towards the center of the circle, that's not always the same direction, right? If you're at the top of the circle, that might be down, or if you're at the bottom of the circle, it might be up. Okay, so hopefully you also got a chance to see a little bit of modeling on how to use some test taking skills. Use what you definitely know to be true. See what you can cross out. Okay? So I will post the video, the notes, all on Google Classroom and our website. Please fill out the exit ticket. My last announcement, on Friday we're having lab. So post on Google Classroom tonight will be the lab. Please read that before coming on Friday. The test is next Tuesday.
So now we always have that on Friday.
For the most part, unless it's in class.
But we won't be having it on Thursday.
Not that I know of.